Problem 7 on composite cylinder. A steam pipe having K 45 watt per meter degree Celsius and having 70 mm inside diameter and 85 mm outside diameter is lagged with two insulation layer. The layer in contact with the pipe is 35 mm asbestos insulating material having K 0.15 watt per meter degree Celsius, and it is covered with 25 mm thick magnesia insulation having K 0.075 watt per meter degree Celsius. The heat transfer coefficient for the inside and outside surfaces are 220 watt per meter degree Celsius and 6.5 watt per meter degree Celsius respectively. If the temperature of steam is 350 degrees Celsius and the ambient temperature is 30 degrees Celsius, calculate number 1, the steady loss of heat for 50-meter length of the pipe. Number 2, the overall heat transfer coefficients based on inside and outside surfaces of the lagged steam main. And point number 3, temperature drop across steam pipe, asbestos and magnesia insulation surfaces respectively. So in order to solve this problem, let us first draw the schematic. In this problem, there is a steam pipe represented by its material A, and this steam pipe is carrying steam inside. Having its heat transfer coefficient H infinity I and temperature as T infinity I. And the steam is represented by red color circle. Then this steam is covered with asbestos insulation represented by B. And finally, this asbestos insulation is covered by further magnesia insulation represented by material C. So this forms a composite cylinder, and outside it is exposed to the ambient air. Let's say its heat transfer coefficient is H infinity O and its temperature is T infinity O, and the presence of ambient air is represented by a thin fluid film represented by the blue circle. Now in this case, T infinity I is greater than T infinity O because inside fluid is steam and outside fluid is ambient air. So by virtue of this temperature difference, heat transfer will take place from inside to the outside. And let's say it is being transferred at the rate Q. Let inside radius of this steam pipe is represented by R1, outside radius is represented by R2. The outer radius of asbestos insulation is represented by R3, and finally the outer radius of magnesia insulation is represented by R. And temperatures at these radiuses are represented by E1, E2, T3 and T4 respectively. Now, as heat transfer takes place from inside to the outside, so by virtue of the thermal resistances offered by different fluid layers and solid materials, temperature drop will take place from inside of the fluid material to the outside of the fluid material. And this is nothing but temperature profile. And we know for cylindrical surface, the shape of the temperature profile is logarithmic in nature. So this way, I could represent all the required parameters affecting heat transfer rate in case of a composite steam pipe. Let's say thermal conductivity of the cylinder is Ka, of asbestos insulation is Kb, and of magnesia insulation is represented by Kc respectively. Now let us draw the equivalent electrical circuit for this system. So there is a heat transfer by virtue of temperature difference at the rate Q. The first thermal resistance will be offered by steam between temperatures T infinity I and temperature T1, and it is represented by RT infinity I. It will be a convective thermal resistance. The second thermal resistance will offered by the material of the steam pipe between temperatures T1 and T2. It will be conductive thermal resistance represented by RT1, or I can also represent it by RTA. The third thermal resistance will offered by the material of asbestos insulation between the temperatures T2 and T3. Once again, it will be conductive thermal resistance represented by RTB. The fourth thermal resistance will be offered by the material of magnesia insulation. It is also conductive thermal resistance represented by RTC. And finally, the thermal resistance will be offered by the air film between the temperatures T4 and T infinity O. It will be convective thermal resistance represented by RT infinity O. And finally, heat will be dissipated to air. So there will be total 5 thermal resistances. 3 will be conductive in nature, and 2 will be convective in nature. Now let us enlist all the given things. So many data is given here. The value of so many data have been given. So the very first data is given as the inner radius of the steam pipe. So it is the diameter of the inner radius, inner diameter of the steam pipe is given as 70 mm. I am interested in radius, so it will be 35 mm radius and 0.035 meter. Outer radius of the steam pipe is given as 85 mm. Outer diameter is given at 85 mm. So radius will be 42.5 mm is equal to 0.0425 meter. Then R3 is the outer radius of asbestos insulation. So it is nothing but R2 plus thickness of the asbestos insulation. So R2 is 42.5 mm and thickness of the asbestos insulation is given as 35 mm. So this will be 77.5 mm or 0.0775 meter. Then R4 will be outer radius of magnesia insulation. This will be R3 plus thickness of magnesia insulation. So it will be 77.5 mm plus its thickness is given as 25 mm. So it comes out 1025 mm. 102.5 mm. So it comes out 0.1025 meter. So we have found out all the radius values. Then let us enlist the values of thermal conductivity of steam pipe material given as 45 watt per meter degree Celsius. Thermal conductivity of asbestos insulation is given as 0.1 watt per meter degree Celsius and that of magnesia is 0.075 watt per meter degree Celsius. And length of the pipe is given as 50 meter. Then convective heat transfer coefficient of hot fluid is given as 220 watt per meter degree Celsius and that of outer air is 6.5 watt per meter degree Celsius. Apart from this, steam temperature is given as 350 degrees Celsius and air temperature is given as 30 degrees Celsius. So let me check the values. Okay, so we have summed up all the values correctly. Now let us make some assumptions. So number one assumption is one-dimensional steady state heat transfer. And what is that heat transfer direction? In radial direction. We are considering heat transfer only in radial direction in cylinder. There could be tangential direction, there could be azimuthal direction, but we are considering heat transfer only in radial direction. No heat generation. Within the cylinder, within the pipe. Then, now the third very important assumption is that here the composite cylinder is composite pipe, which is also called as lagged pipe is there. So different material layers are in contact, like steam pipe material, asbestos material, followed by magnesium material, and they are in contact with each other. So because of imperfect contact, thermal contact resistance may come into picture. But the problem statement does not talk anything about thermal contact resistance, so we will neglect it. So the assumption number 3 will be no or sorry, no or negligible thermal contact resistance. This is very important assumption. Whenever composite structure is coming into picture, please take care about the thermal contact resistance, whether its value is given or not. Then constant properties of material and fluids. What does it mean? K and H values are constant. These are the important assumptions. Now, temperature difference is very high, so heat transfer can take place by radiation as well. So we will neglect this. No heat transfer due to radiation. So these are the assumptions involved in our problem. Now let us enlist what is to be found out. So the first thing we are supposed to find out is heat transfer rate. Second, overall heat transfer coefficient, and third one, temperature drops. So let us enlist them one by one. So the Q value, second one is overall heat transfer coefficient, and it is asking you to calculate overall heat transfer coefficient based upon the inner diameter and based upon outer diameter. And third thing, it is asking to calculate temperature difference across the various material layers. So it is nothing but T1 minus T2, T2 minus T3, and T3 minus. Now let us do the detailed calculations. Now since we have assumed one-dimensional steady state heat conduction, so under one-dimensional steady state heat transfer, the rate of heat transfer from fluid to the steam pipe to the asbestos layer to the magnesia layer to the cold air is going to remain same. So mode of heat transfer will be different. If fluid and solid surfaces are there, it will be by convection, and between solid surfaces by conduction. So how can I sum up this? Rate of heat transfer will be equal to rate of heat transfer from steam to the cylinder surface, steam pipe surface, equal to inner surface of the steam pipe to the outer surface, equal to outer surface of the steam pipe to the outer surface of asbestos insulation, equal to the rate of heat transfer from outer surface of the asbestos insulation to the outer surface of magnesia insulation, equal to the rate of heat transfer from outer surface of the magnesia insulation to the cold air. So there will be total 5 rate of heat transfer. This will be by convection, this will be by convection, and these 3 rate of heat transfer will be by conduction. Now let us write down the expressions for these rate of heat transfer in terms of temperature difference and thermal resistances. So this will be T infinity I minus T1 over thermal resistance of steam fluid film will be equal to T1 minus T2 over thermal resistance of steam pipe equal to T2 minus T3 over thermal resistance of asbestos insulation equal to T3 minus T4 over thermal resistance of magnesia insulation material, and finally T4 minus T infinity O convective thermal resistance of ambient air. Let's say this is equation number 1, equation number 2, equation number 3, equation number 4, equation. Now question comes, what will be the expression of RT infinity I, RTA, RTB, RTC and RT infinity O? So as you can see here, RT infinity I and RT infinity O, they are convective thermal resistances. So they can be represented by 1 upon H into area. But what about RTA, RTB, RTC? They are the conductive thermal resistances offered by cylindrical wall. And what is the expression for cylindrical wall thermal resistance? So here, if you are able to remember it, it is well and good. Otherwise, it is always suggested to refer data book. In data book, the expression for thermal resistance offered by cylindrical wall is given, and it is 1 upon 2 pi KL log of R2 by R1, where R2 is the outer radius, R1 is the inner radius. So It is highly recommended you please refer data book, heat transfer data book. Okay. So after referring data book, where RT infinity I is convective thermal resistance of steam, and it can be given by, this formula is also given in the data book, 1 over H infinity I into AI. So RT infinity I over 1 over H infinity I into the area of cylinder will be its surface area 2 pi R1 into L will be equal to, let us put the values, 20 into pi, and its inner radius is 0.035 and length of the cylinder is L. So it comes out RT infinity I is equal to, this value I could calculate, 4.134 into 10 to power minus 4 degrees Celsius per watt. Then RTA conductive thermal resistance of steam pipe material, and it can be given as, from data book I am done. If you don't remember, please refer the data book. 1 over 2 pi K will be thermal conductivity of steam pipe into L into log of R2 over R1. Let us put the values of all these parameters. RTA is equal to 1 over 2 pi. The value of AA is 45 watt per meter degree Celsius. Value of L is 50. Log of R2 radius is 0.0425 over 0.035. After calculating, this value comes out 1.373 into 10 to power minus 3 degrees Celsius per watt. Similarly, RTB will be conductive thermal resistance of asbestos insulation. Once again, it will be given by, for cylindrical wall, 1.2 pi AB into L log of R3 over R2. See how I am taking this R3 over R2. So if I am talking about the thermal resistance of this asbestos insulation, so R3 its outer radius and R2 is its inner radius. This R3 is outer radius and R2 is inner radius. So that radius is coming into picture. Now putting the values of all these parameters, RTB 1 over 2 pi, the value of KB is 0.15 watt per meter degree Celsius into L is 50 log of R3 is 0.0775 over R2 is 0.0425, and this comes out 0.0127 degrees Celsius per watt. In the similar fashion, I can calculate RTC, that is conductive resistance for magnesia insulation, and this can be given as 1 over 2 pi ACL log of R4 over R3. Taking the values of all these parameters, 1 over 2 pi, the Kc value is 0.075 into 50 log of R4 is 0.1025, R3 is 0.0775. Solving this will give me the value of RTC, excuse me, and this comes out RTC as 0.1187 degrees Celsius per watt. And the last value of thermal resistance is RT infinity O, that is convective thermal resistance of ambient air, and it is given by 1 over H infinity O into AO is equal to 1 over H infinity O 2 pi R4 L. So putting the values of all these parameters will give me H infinity O is 6.5, 2 pi, the value of R4 is 0.1025 and value of L is 50. So this value finally comes out 4.777 into 10 to power minus 3 degrees Celsius per watt. So this way I could calculate the values of all thermal resistances. Now this is the major portion of any numerical, calculating individual thermal resistances correctly. Now after calculating individual thermal resistances, let us calculate the total thermal resistance. So this will be nothing but summation of RT infinity I plus RTA plus RTB plus RTC plus RT infinity O. Let us put all the values. 4.134 into 10 to power minus 4 plus RTA is 1.373 into 10 to power minus 5. Let me check. Oh, extremely sorry. This value is 10 to power minus 5. Then RTB is 0.01274. RTC is 0.01187, and finally RD infinity O is 4.777 into 10 to power minus 3. Summation of all these thermal resistances will give me the value of total thermal resistance across the system wall, and it is 0.02981 degrees Celsius per watt. Now we could calculate total thermal resistance, and we have the expressions for individual thermal resistances. Individual heat transfer rate through the steam pipe, asbestos insulation, magnesia insulation, and cold air. Now I could calculate the value of steady loss by using either of the equation from 1 to 5. But once again, what is the problem? I don't know the values of T1, T2, T3, T4. However, I have been given the values of only T infinity I and T infinity O. So what is the solution? Solution is to express the value of Q in terms of known temperatures T infinity I and T infinity O. And whenever I write the expression for heat transfer in terms of, let's say, extreme values of temperatures, that is initial and final. So under such condition, all the thermal resistances occurring between those two extreme temperatures get added up. Same thing we are going to do here. RT infinity O, nothing but T infinity I minus T infinity O over total thermal resistance. Now I have the values of all these parameters. 350 minus 30 over 0.02981. So this value comes out the value is coming out 10734.65 watt. So this is the steady loss from the steam pipe, and this is answer number 1. The next parameters are UI and UO. So based upon inner area of pipe, what is the relationship between overall heat transfer coefficient and total thermal resistance? It is nothing but UI into AI is equal to 1 upon summation of total thermal resistance. So UI into AI is nothing but 2 pi R1. The value of R1 is 0.035, value of L is 50, and value of the total thermal resistance just now we have calculated 0.02981. So from this the value of UI comes out at it 0.5 watt per meter square degree Celsius will be the answer. Similarly, UO I can calculate overall heat transfer coefficient based upon outer area. So UO into AO over 1 upon summation of RT. UO into 2 pi. RO is nothing but R4 and its value is 0.1025. The value of total thermal resistance is 0.02981. So from here the value 1.0417 watt per meter square degree Celsius. This will be answer number 2. And finally, let us calculate the temperature drops. T1 minus T2, T2 minus T3, and T3 minus T. Now, how to calculate this? So, to calculate these temperature drops across the solid surfaces, let us get back to our equations. So, as you can see here, in equation 2, 3 and 4, these temperature drops are appearing. So if I individually recall rate of heat transfer equation, that means if I individually recall equation number 2, equation number 3 and equation number 4, I am able to calculate these temperature drops because I know the value of RTA, RTB, RTC, and I know the value of Q. So only unknown will be temperature drop across the surface. So let us do one by one. So first, recalling equation number 2. What is that equation? Q is equal to T1 minus T2 over RTA. The value of Q is 10734.65. 10734.65 is equal to T1 minus T over the value of RTA is 1.373 to 10 to power minus So the value of temperature drop across the steam pipe will come out 0.147 degrees Celsius. Then recalling equation T. So Q over T2 minus T3 RTB 10734.65 is equal to T2 minus T3. Value of RTB is 0.01274. 0.01274. So the value of temperature drop across the asbestos insulation surface comes out 0.76 degrees Celsius. And finally, recalling equation 4. Which happens to be Q is equal to T3 minus T4 over RTC 10734.65 is equal to T3 minus T4 over the value of RTC is 0.01187. So the value of this temperature drop across magnesia insulation comes out 0.42 degrees Celsius. Answer. So please do check the calculations, but process is the same. So this way we could solve the problem.